We shall discuss today several methods of input-output data transfer from external devices. The problem is quite severe here due to wide variety in characteristics in several aspects. Let us see what can be the variations of the characteristics. So 3 points have been noted here. One is that wide variety in types. The devices can be electronic, electromechanical, mechanical, etc., with no or little electrical compatibility between the CPU. There is enormous variety in speed as well. The transfer rate can be from few bytes per minute to several kilo or megabytes per second. So few bytes per minute is in the case of a keyboard, and several kilo or megabytes per second in the case of a secondary storage disk. Okay. There can be wide variations in data format as well. For example, in the case of a keyboard, there is an 8-bit data with a leading and a trailing bit, whereas in the case of a input from say disk, it's a half a kilobyte data with leading information, trailing informations, including error correcting information. Okay, therefore, all these have to be taken into consideration when I/O is interfaced and input-output data transfer is considered. Now, these are the modes of data transfer that we will discuss. There is programmed data transfer, interrupt-driven data transfer, and direct memory access. The direct memory access can be in the cycle stealing mode or the burst mode. We shall discuss these three techniques one after the other. First, let us recall the way that memory was interfaced. First, we see that how an I/O device is interfaced. Before that, let us see that how we consider the memory was interfaced. Here, the problem is much less severe since the technologies are same. The differences of speed are there, and that is managed by means of handshaking signal. Here you see that from the CPU we have the address bus, the data bus, and the control buses. In the case of a memory, they are more or less directly connected with a memory chip, and we have seen how several memory chips can be combined together, can be arranged to get a higher order memory. Now, let us come to that interfacing an external device. Okay. You see here that we have the CPU, okay, that address bus, the data bus, and the control bus is there. We have to connect an external device. Say this is an external device. This device has its own control logic, electronic control logic. It has this buffer where the data can be there, and it has this interface with that environment from where the data will come. That interface possibly will have circuits like analog to digital or digital to analog converter and some such circuits. Okay. The data that comes over to here after conversions is assumed to be in that buffer. The detailed device technology, etc., is beyond the scope of our lecture, and therefore we will leave only at that there is a control logic, there is a buffer, and there is an interface. Now, to connect this external device to the CPU bus, what we need is an I/O module. Sometimes it's called an I/O interface or an I/O port. Now, let us see what is there in that I/O module. In a simple situation, that I/O module will consist of only two registers. Say control CS, the control command and status register, and the buffer register. This interface is now to be connected with the system, right? And therefore, this interface is connected to the data bus. The data is transferred to the data bus. It is connected to the address bus, where naturally an address decoder will be there, and this register and this register should be addressable by the CPU instruction. Now, one thing is that we can address these two registers as simply as a memory register. In that case, these two signals should be say memory read signal, and here it should be memory write signal that will be connected. Now, if this address decoding circuit chooses these two register and it is chosen as a memory read or a memory write by means of the CPU, then these two are called that memory mapped I/O. The entire interface is memory mapped. In this case, what actually happens is that, say, as if we have that entire memory, say this is the memory of the computer. Say this is the addressable portion that the CPU can address. In this case, then when we are talking about a memory mapped I/O, some portions of the memory somewhere, say these portions of the memory, we choose and map to I/O. That is called memory mapped I/O. Here all the device registers, by that I mean that interface registers, are mapped here. That means from this to this, a portion of the addressable memory space is dedicated for the I/O purpose, and such a situation we call a memory mapped I/O. And in that case, like any other memory locations, that memory read and memory write signals are used along with the address bits to address the registers in that interface. Now, this is one situation. Another situation is that instead of this memory read and memory write, there are two more signals that the CPU possibly can issue. Okay, one is called I/O read and another is called, say, I/O write. In this case, the addresses of these command and status registers and the buffer registers are totally different from the memory and it's non-overlapping. Say this is the memory, in this case, that if we use that I/O read and I/O write, then the total I/O space, say this is the I/O space, is different from the memory space, and any registers in that I/O, that means interface, is mapped into this I/O space. Okay, some address here, some address here. Possibly this will be the command and status, and this will be the buffer register. Now, how do I distinguish between the memory space and the I/O space? That is distinguished by means of whether you are using memory read, memory write, or I/O read and I/O write. Okay, and say what is the distinction? How the CPU distinguishes them is by means of that instructions. For example, if we are having memory mapped I/O, basically we are using same space as memory, part of it. All memory instructions can be used here. That means we can use move, transfer, load accumulator, store accumulator instructions to transfer data from and to the command as well as the status registers. Okay, if we are using memory mapped I/O. And if we are using I/O mapped I/O, basically the instructions that we are using is in, out, and these in, out instructions will automatically tell the control of the CPU to issue I/O read and I/O write signals as is necessary. I/O read for reading and I/O write for writing. Okay, in that case, we are mapped automatically onto the I/O space. Now, one can choose the memory mapped or the I/O mapped I/O whenever, say, I/O devices are being interfaced. It is up to the designer to choose. Okay, whether one should use a I/O mapped I/O or memory mapped I/O. Now, let's come to the rest of it. The situation is this. Say, let us see that how the I/O data transfer takes place. Okay, let us take a simple example. Say, like a simple device like keyboard, where you press a key and an 8-bit code comes into the buffer. Okay. Now, here you have to tell the device okay, that you need to read one character. For that, the CPU issues either either a transfer or the out instruction. This bit is set to 1. Okay, so command bit, say we set this bit to 1, automatically telling the device which is sensing this bit that one input is expected. Okay. Now on that, the device will take that data from that external environment, put into the buffer here, and that will be transferred into the buffer. And at the same time, the status register, this will be set to 1. That means initially, say both of them were 0. The CPU commands the device by setting this bit to 1, saying that it needs the data. The device, on creating the data, sends the data to this buffer, okay, and at the same time put a 1 in the status register. That means the status register is changed from 0 to 1, indicating that the data is already in the buffer. Okay. Now what the CPU has to do now, that after sending the command into the command here, okay, is to go on checking the status to see whether the buffer, the data is there. That means whether the external device has put into the IO port buffer the data that it needs. Now when it finds that it is 1, then the CPU then reads the data from the buffer into a CPU register. This is what we call the program controlled IO. Okay? That means the situation is somewhat like this. Say we want to, by programmed IO, we want to read a block of data. Okay. Then the CPU first will issue a read command to the IO module by putting that command bit 1. Then it will go on, it will read the status from the IO module by reading the status bit, whether it has turned out to be 1 or not. If it is not ready, then it go back over to here, read the status once more. That means it remains in a very tight wait loop, okay, till it finds that data is ready. Now two situations may turn up, that data could not be read and an error conditions is there. In that case, the CPU should go on examining that what is the error situation. If the data is ready, then the data word will be read from the IO module into the CPU register, and possibly in that case write the word into the memory location. And since we are thinking of, say, transferring a block of data, if the count, that means the total block, has not been transferred, in that case it will go back and issue the read command once more. Therefore it will be in a loop to transfer a block of data, and once a command is given to read one data word or a data byte, say, it has to go on checking. That means it has to wait in a very tight wait loop over here, essentially doing nothing very effective. Essentially the CPU is busy here only to check whether the data has been made ready or not. Okay. Therefore it is, so to say if it is a very slow device, right, say keyboard, then it is, you can see very easily, it is a total wastage of CPU. Even for example, if it is a disk, the difference is timing is micro to nano. You can immediately say it's a 10 to the power 3 times difference, and waiting in such a tight wait to CPU just to check whether the data is ready or not is essentially wastage of CPU time, and therefore we should try to improve here that what can be done to improve the situation so that the CPU do some effective work, okay, instead of just waiting like that. Anyway, this is what we call this programmed IO, right? Now, here we have taken a simple situation that we have a command and status the same mixed into one, because we are needing only one bit and possibly an error bit here to indicate that there is an error in that status register. But in many situations, that the command and the status registers are different, and in cases where the device is more complicated, there will be naturally more status and other registers involved in it, and the buffer registers, instead of say 1 byte or 1 word, possibly it will be several byte or several words long. Okay. Now, as I was telling, that the situation here essentially is that this is a very useless wait loop for the CPU. What can be done about it? The simple situation is that an improvement can be that why wait? Why not, after issuing the command here, that you read some data, or in the case of a output device, that you write data into the device, okay, or write data, tell the device to write the data into the environment, okay, that the CPU goes on doing something else. Okay, it just gives a command that you do the job, the interface, through the interface to the device, that you do the job, and then it flies off to some other program and starts executing some other program, which will be an effective utilization of the CPU time. Now, this interface, when the device tells that the status is 1, okay, that means the job entrusted with the device is over, the status is 1, then a signal is sent to the CPU, which we call that interrupt request. Okay, we call that interrupt request. That a signal is sent to the CPU to a particular input to the CPU, which we call that INTR or interrupt. Okay, that the work is over. On getting that interrupt, waiting for some time, okay, that means waiting till the end of the present instruction that the CPU is executing. Let me repeat that, waiting till the end of the present instruction that the CPU is executing, an interrupt acknowledge is sent to the IO interface, the hardware handshake, telling that your request has been exceeded, that it's known that the data is ready in the buffer, and then the CPU takes care of the data. That means only then it possibly takes the data from the buffer into the CPU register, and if necessary does some computations here and then send it to the memory. That situation is depicted here. Okay, that situation is depicted here. You see that here what we have done is the difference between this programmed I/O and we call it that interrupt driven I/O. What have that done is that issue read command to the I/O module, that remains the same as it's over here, and after issuing the read command, the CPU breaks from here and starts doing some other work. Okay, simply jumps from here and starts doing some other work. On getting an interrupt, an hardware interrupt, the CPU comes back into this program portion. This is called that interrupt handler now. Okay, that interrupt, on interrupt, this particular portions of the program is executed, and such a program which is executed on occurrence of an interrupt, when the CPU acknowledges it, is called an interrupt handler. Then it reads the status from the IO module to check that whether there is an error condition or not. If there is an error condition, that is taken care of. If there is no error, then the word is, or the byte, whatever it is, that read from the IO module, write the word in the memory. I am assuming that no processing is being done over here, and then checks whether all the bytes for the block transfer has been done or not. If not, then it goes back and issue the read command once more, and then goes over to do other useful work. Okay. Now you can see that the CPU is not waiting anymore in a very tight waiting loop. It is essentially going from breaking out of this, doing some useful work, and coming back on a hardware interrupt. Okay. Now, this is done on this interrupt request. Okay. Now let us see the situation in terms of our program execution. What happens, right? What happens essentially is this, that say this is a program that is the CPU is executing. Here that issue read command for the input device or write command from the output device has been issued. As we have seen that the program count, and this is the next instruction, as we have seen that while executing a program, the program counter always contains the address of the next executable instruction. Say the next executable instruction here is at the location 62AB. Now say, I should say, let me repeat that somewhere here, okay, somewhere before this program execution, that device was told to read. That means this control and status station, this bit was made 1 somewhere outside this program, and the CPU has come back, has started executing this program. Now this program is being executed statement by statement, say this is executed. Now when this program is being executed, at this point say that interrupt has come, okay, that interrupt has occurred. Now you can see, as I have said, that occurrence is asynchronous with the execution of the program. The device was excited quite earlier, CPU is executing this, possibly when this instruction was being executed, that is this instruction, when the program counter is holding the address of the next instruction, which is 62AB, and the interrupt has happened. Okay. Then after the execution of this instruction, the present program counter is stacked. So 62AB will be stacked, and another register generally we call the processor status word. Okay, we call this is a processor status word that is also stacked by means of the hardware through the hardware stack pointer, just like that we discussed in the case of a subroutine jump, that the program counter is stacked in the system stack. Here the program counter and the processor word is stacked one after the other, and the control of the execution of the program is now transferred to interrupt handler. Now since we are thinking in here a single device as if that is connected to the CPU, let us assume here that there is one interrupt handler whose address is predefined by means of hardware inside the CPU, and let that address be HC54. Okay. Then the program counter will be loaded with HC54, which essentially means that the program execution will start from here, which is our interrupt handler. Now the interrupt handler routine is executed. At the end, a return from interrupt will be executed, like say return from subroutine return. The return from interrupt does this, that it takes the processor status word out of the stack and loads it back into the processor status word. It takes the program counter content and loads it back into the program counter, which means now the program counter, since it is now pointing to 62AB, the control returns to this instruction and the executions of this program starts once more. Okay. Now as I am saying, the processor status word is nothing but a word, okay, which contains the overall status of a program being executed, right. Therefore when I am moving from the program that is being executed on interrupt to that interrupt handler, we are assuming here that the address of the interrupt handler is known. That means it is here as if HC54, which is loaded to the program counter. This interrupt handler routine will be executed, and on return from interrupt, the old processor status word will go back to the processor status word, which is corresponding to this program environment. The program counter old value will go back to the program counter. Therefore program counter is now pointing to this, and then the executions of the old program will start. Okay. Now let me repeat once more. The occurrence is asynchronous. That means the occurrence of the interrupt is asynchronous. Therefore we do not know when this program is executed at what point that interrupt will come, but irrespective of at what point that interrupt comes, on getting an interrupt, okay, and CPU acknowledging the interrupt, on getting an interrupt for this device and CPU acknowledging the interrupt, okay, the control will always jump to its corresponding interrupt handler of the device. That interrupt handler will be executed, and on return from interrupt, the resumption of the executions of the program at the break-off point will start. Okay. This was more or less is a situation as was done in the subroutine jump and return. Only situation that the only difference is that we as a programmer knows exactly where the subroutine call instruction exists. Okay, that we know that at this point that subroutine jump will take place. Okay, but in the case of an interrupt, external interrupt like this, okay, the the programmer or the even the CPU doesn't know at what instant of time that interrupt will arrive. Okay, but as the interrupt arrives, the interrupt is taken care of by means of the interrupt corresponding interrupt handler, the way that I have told. Okay, now we'll see later on situations that there can be interrupt within interrupt when more than one devices are there. Let me tell you that in that case, for example, if there is an interrupt within interrupt, then from there it will go to another interrupt handler, will execute that interrupt and will possibly come back over to here once more on the end of that interrupt. Then this portion will be executed and the control comes back over to the original point of break, right. Now, before we proceed further, let us see that what when we say that is a processor status word, PSW, let me write it the full word for it. PSW is essentially processor status word. Now, here I have assumed, say that we have a 31-bit program counter. I think it turns out to be 4 GB of main memory, addressable main memory. Now, here is the processor status word. It contains, you see, the carry, overflow, sign, and parity bit, okay, at any instant of time, right. Therefore, as the arithmetic and logic units computing values, okay, the carry, overflow, parity, etc. is being generated in that flag flip-flops, as we said earlier, that is as a part of, so to say, the processor status word. Now, there is one bit which you call that interrupt bit. It says that it's interrupt enable or disable, which means, as I said, that here that it interrupts, okay, but here we can keep one bit. If that is 0, then no interrupt request is honored, okay. This is, and when it is 1, only that then that interrupt request is honored. This bit is called that interrupt enable disable bit, okay, and that's also is a part of the processor status word. We'll see later on that when multiple devices will have to take, in that case we'll have to decide about the level of interrupt of the different devices and therefore their service routines, that either it can be taken as a number which determines the level, or it can be an interrupt mask, okay, that is kept here. And what this interrupt mask means will come to when we are dealing about more devices that is connected, okay, as an interrupt driven input output devices, okay. One important point here is that there remains another bit we call that user supervisor mode. This bit is very important, and we'll see later on when we'll be discussing that operating system that what is the significance of its beta. This means if that bit is say 1, right, then it is in the user mode, and when this bit is 0, then it's called the supervisor mode. Now, the situation is, as I told you, that On getting an interrupt, the CPU changes into that interrupt handler with a new processor status word loaded. But if we choose when the new processor status word is loaded, this processor status word, when it is being loaded, that if this interrupt, the user supervisor mode bit is 0, say, indicating that is a supervisor mode, right? In that case, basically the system is moving from making state change. That means it's from user mode, it is moving to a supervisor mode. And in the supervisor mode, the CPU can execute many privileged instructions. And what are these privileged instructions are, that we'll be discussing at the time of when we'll be discussing that operating system, right? Now, I'm saying that, so this 0 is user, 1 is supervisor. It could be the otherwise also. But the important thing is that on changing, on interrupt, the status, one can jump from user mode to supervisor mode, and when it comes back to the original mode, original state, from where the control flew off. Now, regarding that interrupt mask bit, we'll talk a bit later on. Now, let us come to what will be the interrupt handler structure. Say we have entered that interrupt handler here. Basically, you see that in situation that the system will not be in that interrupt handler quite long. Mostly these interrupt handlers, device interrupt handlers are small, and in that case, a complete context switching, as we call, that means a complete change of total environment under which the program is being executed need not be changed. What exactly is we mean by context switching? We'll see once more when we discuss the operating system. But some changes naturally have to be done. For example, that when it changes, if the interrupt handlers wants to use these registers, the register values have to be saved, in the memory location. Then one important aspect is that when the CPU enters that interrupt handler, the interrupt is automatically disabled. That means there is no interrupt to be accepted until and unless you say that you accept the interrupt once more. The programmer says by means of program instruction that interrupt is accepted once more. That is, for example, here the save registers. Then if you want that interrupts be accepted once more within the interrupt handler, that means you will allow interrupts within interrupts, then you issue an interrupt. You can write an interrupt enable instruction here. The instructions may be, say, enable interrupt. Then the actions are taken. Then once more you have to go back. Therefore, you disable interrupt here, restore all the registers that you had saved, and then make an RTI, return to from where the control entered the interrupt handler. Therefore, this is more or less the structure of an interrupt handler in general. Now the question comes, right, that when exactly, say, when this interrupt comes, and I say that interrupt may come asynchronously. The CPU is executing instruction in the memory. The interrupt can come any moment, but when the CPU accepts that interrupt, that is, let us examine the instruction cycle. Here is the instruction cycle I have shown. The instruction cycle starts here. Is a fetch instruction, decode instruction, so the fetch operand, there may be more than one operand, then the execute instruction, so store result, and here where is that interrupt is then accepted if the enable interrupt is there. That means interrupt is enabled, then this is the interrupt breakpoint where that interrupt is accepted, and then from here that execution of the instruction starts at the interrupt service routine. Therefore, after this the next fetch instruction that is executed in that interrupt service routine. The first instruction of the interrupt service routine will be fetched by means of this fetch instruction. Therefore, this is the entire instruction cycle is over. Interrupt is accepted here if the interrupt is enabled, and then this fetch instruction is the fetches instruction of the first instruction of the interrupt service routine. That is the situation so far as the acceptance and processing of interrupts is concerned. Now, let's see. Here I have shown this diagram. That means this instruction has been executed. Here the interrupt has been sensed. Then the control goes over to that interrupt handler if the interrupt is accepted, and this is the next instruction that will be fetched by the next instruction cycle. Now, after that, let's see few points that I would like to clarify if I have missed in my course of this lecture. That here is the external device we have talked of. We said that there is whatever I said for an input device or an output device is similarly true for an output device or an input device. For example, see if there is an this is an input device, that means data is coming into the buffer. We say that this is my command, and say this is a status, sorry, this is a command and this is the status. If you want to read something for that input, then this command bit I put to 1. The device puts the data into the buffer, puts the status bit, okay, on getting the status bit, or the interrupt, we read from the buffer. In the case of an output device, it will be similarly true. That means that command bit will be set to 1, CPU will send the data into the buffer, and on consumption of the data from the buffer by the device controller, the device controller will set this status bit to 1. Okay, that is why I am saying that whatever discussions we made in terms of input device is similarly true for output device and vice versa. Another important point that I would like to point out, that we have, say, put the control and status register, command and status register as a single register. But in the case of the devices which are a little bit complex, like say the disk drives, etc., in such situation, that command and the status registers may be different. Okay, there may be a command register separate and the status register separate, because many commands can be there. In the case of a disk drive, say, for example, the search a surface, then seek a sector, so on, say the read, write. Therefore, there may be a separate command register. Similarly, the status registers also can be a separate one, because the apart from the data that is put into the buffer, what is the status of the read or write, so for example, or search or seek, okay, that is put into the status register as a combination of bit. And if there is an error, that error condition is also put into the status register as a combination of bit. That is why sometimes the command and status registers may be different. The buffer register here, I showed it to be a single byte or word, but in many cases, okay, like say for example, once more a hard disk drive or floppy disk drive, that interface, that buffer may be, say, quite big. It may be, say, half a kilobyte, even several kilobytes, so that the data transfer between the CPU and that port, okay, that interface module, can be made fast. Okay, that is why sometimes the buffer register, instead of a single word or a byte, it can be constituted out of many words or bytes. Okay, sometimes as big as half a kilobyte or say 1 kilobyte. Now that is the third point, right? Therefore, what I intended to mean that our emphasis essentially of this discussion had been that that the protocol of data transfer between the I/O module and the CPU module. In the case of an interrupt service routine or that interrupt handler, we was just discussing about as if a single device has been connected to the CPU. Naturally, it cannot be the situation that a CPU to a CPU only a single device has been connected. There may be many devices that are connected to the CPU, and therefore we'll have to tackle the case of interrupt handling where more than one devices is connected to the CPU. That is the discussion we will be making in the next lecture. Thank you.